Rosenblatt.
In place of Detlef Koschny.
Thank you. And the title is Phobos Sample Return, a study for a joint Russia-ESA mission to the moons of Mars. And this is a 30-minute talk.
Yes, thank you. Okay, Detlef Koschny is ESA scientist in charge to study a Phobos sample return mission. And he apologized not being able to come to give this presentation, and he asked me to give it. So I will try to do my best to present you this Phobos sample return design mission. And so this is the Russia-ESA mission to the moon of Mars, and the science requirement comes out from a science study team with several European scientists and with key scientists from Russia also, of course, and with the help of ESA engineering team. This mission design is the follow-up of previous studies and from already 5 years ago, 2011, with the Mars Moon Sample Return design mission. And here, this is a very nice image illustrating this mission with a landing on the surface of Phobos and the Earth return capsule containing the sample. And so following this first study mission from 2011 to 2012, there is the footprint design mission study in 2014 with already a study science team. And here this is an illustration because footprint actually is not an acronym, but it's just to give an idea that to leave a footprint at the surface of Phobos. And so this now the Phobos sample return mission I will present you. It is the following of these previous studies, and it is within the ESA's robotic exploration program, and it is studied over the last 2 years. And if it is accepted, this Phobos sample return mission could follow the ExoMars 2020 mission. So this is for the programmatic aspect. And so the science goal, it is not only to be able to understand the origin of the Martian moon or how the Martian system formed. It goes beyond with how the solar system formed itself. Because if we were able, for example, to show that Phobos and Deimos were formed from a giant impact, it will support the NICE model, which predicts large impact within the solar system at the early stage of its formation. So as we have seen this morning, there is different hypotheses for the origin of the Martian moon. And there is one we didn't speak about too much. This is the Coformation, which assumes that, in fact, Phobos and Deimos are building blocks having formed Mars. And if it is the case, the sample should have the same or similar composition to Mars. And so a comparison between the Phobos sample and the Martian meteorite could provide interesting information to test this hypothesis. So in the contrary, if it is an object captured by Mars, so the Phobos sample should have a composition more closer to composition of asteroid. And finally, as we have discussed a little bit this morning, the impact of a large body onto Mars, we should expect, in fact, to have a composition with Martian composition and impact or with a non-composition, so maybe asteroid composition or others. We can wonder now, why not to get sample from Deimos? After all, Deimos is much easier to get and to bring back sample to the Earth because this is less inside the gravity field of Mars than Phobos is. But as we can see from these images, Deimos surface is covered by a thicker regolith than for Phobos. And so this is a more long history of deposition that could mask, in fact, the true composition of Deimos. And we could expect on Phobos a more pristine surface that could reveal more really the composition of the body. And so the goal of the Phobos sample return mission, this is to get in the order of 100 grams of samples from the Phobos surface. And in addition, to provide enough context information to be able to properly interpret the sample analysis results. So why do we want a sample return? After all, we could make in situ analysis. Yes, but if we want accurate measurement, we need big machinery like this one in lab on the Earth, and this is very obvious, but this is not possible to launch them in space, and especially at the Martian system. And to illustrate the fact that we really need accurate measurement, here on the left, this is a plot showing the variety of composition among meteorite material, and with the in-flight instrumentation that we can get with error bar, this is this kind of measurement, and you can see that this is not possible to decipher between this variety of composition. And so this is why we need to return sample to the Earth to get analysis with this machinery in order to get much better error bar in order to be able to decipher between these different compositions. And in addition, it doesn't exist, at least so far, in-flight instrumentation for precise dating of the sample. And this is something very important because we really need to date the formation of Phobos and Deimos, especially in the giant impact scenario. So the scenario that has been studied, these are first a joint baseline, joint between ESA and Roscosmos, with ESA contribution for the lander and for the Earth return capsule, and Roscosmos for the propulsion module and the Earth return vehicle, sorry. And there is an alternative with just a shift between the lander and the propulsion module between the two space agencies. And the third, this is an ESA standalone mission, so ESA will provide all the pieces of the spacecraft in this case. So with the science study team, we have provided science requirements, and the result is that is in three main mission phases. The first, this is the global characterization. That means to measure the properties of a large part of the object, so here Phobos, on a global scale. This is illustrated here. And the second phase, this is local characterization, which is the characterization of at least 3 dedicated areas, which are being identified from the global characterization phase as potential sampling sites. So it means that we need a more close-up flyby of the spacecraft just above the surface of Phobos. And the last phase, this is a sample context itself, so after the landing, in order to provide measurement at the actual sampling site. And so the science requirements give, in fact, requirements for the percentage of surface coverage for each of its phase of the mission, and require resolution for this kind of measurements. And it has been focused on the visible imaging and also on the near-infrared and thermal infrared measurement. And so these requirements are summarized here in this table. And for the global characterization phase, we need to have the resolution for the visible imagery to be better than 3 meters. Here, when we are talking about the resolution, that corresponds to twice the size of the pixel of the image. And for the near-infrared and thermal measurements, we need a resolution better than 30 meters. And this resolution has to be reached for a minimum surface coverage of about 50%, so half the surface of Phobos, and of course, to cover all the potential sampling area. For the local characterization, we need a better resolution, down to 15 centimeters for the visible imagery, and better than 1.5 meters for the near-infrared data. And we need 99% confidence area of the landing ellipse. And for the sample context, we need, in fact, resolution for the imagery better than 1 millimeter. And so we have also defined other requirements that cover, for example, this just a summary here, sample-related requirements. That means temperature ranges, pebble sizes, and also information concerning the contamination of the sampling site. For the global characterization, in addition to the previous one, we need a spectral resolution requirement. We need a good reconstructed positioning after landing. We need to determine libration amplitude. This is quite interesting for the interior of the body. The shape model also, accuracy. And for the local characterization, in addition to the previous requirement, we need a spectral resolution requirement, like for the global characterization. Also a requirement for the relative 3D topography. And for the third phase of the mission, the sample context requirement, we need information about the regulated size distribution, characterization area before and after the sampling. This is quite important for the contamination problem. And we have also other requirements related to the calibration of different devices. We need to check the success of the sampling. And we also need to know the landing area with an accuracy of plus or minus 50 meters. And so also very important, and this is still under study, this is requirement to curation facility and mainly the problem of contamination, because the device for landing could contaminate the area of sampling. So in the case of ESA Russian joint mission, we could have additional payload because we could have more power, and so we could in fact perform also more interesting global characterization of Deimos, and so to reach the same global characterization of Phobos, so half of the surface covered with the required coverage resolution, sorry. While with the ESA only mission, we could only characterize Deimos for not more than 10% of its surface. And so the science payload here for the spacecraft, so that will land at the surface of Phobos. In the case of the ESA standalone mission, it will be focused on the sample context. And so this is why we need a wide-angle camera, a narrow-angle camera, mid-infrared and visible and near-infrared spectrometer, and this is for the phase of the global and local characterization, especially for the landing site selection. And for the sampling context analysis, we need stereo camera and close-up imager, and especially to perform imaging before and after the sampling, after the landing. And so a radio science experiment is also foreseen in order to characterize the gravity of Phobos, although this is still in study, and especially the choice of the close-up orbit before landing. And in the case of the joint mission, additional Roscosmos Russian science payload are scheduled, but not related to the sample itself, and especially libration amplitude, which is really necessary with the gravity field in order to better characterize the internal mass distribution inside Phobos. And so, so far, in fact, two devices for the sampling mechanism have been studied. So there is a cover, and there is a burst-type sampler, like for the OSIRIS-REx mission, and it has been successfully tested very recently in a microgravity environment. And so to summarize this presentation, this is very short because this is really not my stuff, and I used the slide sent by Detlef, but I will summarize the key point here. So there is at ESA a Phobos sample return mission under study, and there is industrial phase study with two parallel industries, so one in Italy and one in UK. And this parallel study are undergone since last year and are scheduled to finish this year. So depending on the programmatic and the decision at ESA, this mission could be possibly a follow-up mission of the ExoMars 22 program. So this is in the ESA robotic exploration program. The science is mainly driven by understanding the formation process of Martian moons, and beyond, it is within one of the major goals of the exploration of the solar system at ESA. This is to understand the formation of the solar system and the particular very dynamic phase of the early solar system. And so we have already produced detailed science requirements, and I have presented them in this presentation. And we are now reaching a feasible mission scenario. Some were already defined, which allow to return about 100 grams of sample to the Earth. So this is this presentation. I think I have a lot of time for questions.
Is your 100 grams from your one core sample that you showed us? And what depth does that go to?
So as far as I know, for the core, this is not so well studied as for the burst type sampler. Okay, and so I don't know if it's 100 grams can be reached, and I don't know which depth. So
TBD.
This is just for, as far as I know, I don't know if...
Could I just step in and help here? My name's Alistair Wayman. I'm part of one of the study teams. I'm doing the next presentation. The core, well, the samples will come from just one sampled location in both instances with both the core and the rotary brush mechanism. And for the core, it will be a few centimeters below the surface. So it's still going to be quite a high up sample. It's not going to be going a significant distance below the surface.
So that'll get you your 100 grams?
Yeah.
Just a few centimeters?
Yeah.
Okay. Thanks.
Hi, Ben Hockman, Stanford University. I was just curious if you're considering deploying any surface packages while you do the sample collection. Any surface landers, mobility packages to do in situ science?
Again, do you want me to...
like a mascot lander.
I can offer some answer on this. So for the ESA standalone scenario, we wouldn't, just because we're very mass constrained, so we wouldn't have the mass available to do that. For the joint scenarios, the lander module, well, in all the scenarios, the lander module remains on the surface. For the ESA standalone scenario, it dies at that point. As soon as the Earth return vehicle ascends from the surface, the lander's dead. However, for the joint baseline and the joint standalone scenarios, the lander module will operate on the surface for up to 20 weeks after the ERV leaves. The main driver for that is the libration payload, so that we can get the information on the libration amplitude and the internal structure.
Okay, thanks.
Pascal, do you want to comment on the decision schedule to make this happen,
so
both in the joint case and in the ESA only one?
So the next step, this is the end of the industrial studies. So it will be in a couple of weeks. And then at the end of the year, there is the usual science policy committee at ESA that will make a decision, in fact, to continue this science study and technical feasibility. And I think that the decision for the mission will certainly wait for at least next year or the two next year. And it will depend also on the ExoMars mission. This mission has been postponed to 2020. We hope that it will be the last postponed of this mission. And so the next could be this one, okay? But the decision, I think, will be next year or in the next 2 years, not before.
Yeah.
But the study are continuing.
Okay. Do you know if the decision is likely to be affected by JAXA's decision to go forward with MMX or not?
It will depend on the decision to be made in August concerning this mission. Normally, it is scheduled for, the launch is scheduled for 2022. And if it is the case, it will be an impact of this mission, because so far this mission for ESA it's scheduled for 2024 for the launch at the best. Okay, but if the JAXA mission is postponed, So it could be some competition or some effort to join the different studies. So this is not well defined for the moment because it's depending on many things. And we have discussed the previous presentation about European participation to the JAXA mission, but this is something for the moment completely independent to this Phobos sample return mission design.
Okay, great. And one final question: what about the anchoring, the landing gear and the anchoring system? Are you aware of any specific approach to that based on the Philae experience and all that?
So I'll talk a bit about it in my next presentation as well. But for the landing, during the landing, we'll have 4 fixed landing legs, but we'll have a series of hold down thrusters that will fire at the moment of touchdown. They'll give about 140 newtons for about 25 seconds. That should allow us to tranquilize on the surface. And we've got quite a big activity that started within Europe recently to do full-scale testing on that to verify that. We'll also have those thrusters available during all the sampling operations with the robotic arm as well. But yeah, it's certainly one of our concerns following on from Philae. Yeah.
Good. Thank you.